In this video, we're going to talk about initial value problems for matrix ODEs. So I want to do this with an example. So let's suppose that we have the matrix ODE, x prime equals this matrix times the vector x, and we want to find a general solution to this system, find the fundamental matrix, and in part C, solve this initial value problem. So we're given x of 0 is 7, 7, 16, and we want to find what x of t would be. Okay, so pause the video for about 4 minutes and think about how you would start this problem. Remember, when we're solving this, the first thing that we need to do is find the eigenvalues and the eigenvectors of this matrix. So that's what I want you to focus on during this pause. So 4, 3, 2, 1, pause the video for about 4 minutes and try this problem. All right, so hopefully you did that. Hopefully you've paused the video for about 4 minutes to really try to find the eigenvalues and the eigenvectors of this matrix. So it's a bit challenging. It involves the rational roots theorem, but I'm going to go ahead and just say what the eigenvectors and the eigenvalues are. So you should check this. Check that when you use the rational roots theorem here, the rational roots theorem, that we end up getting two eigenvalues, -1 and 5, and then I've written down their corresponding eigenvectors. So -1 has two linearly independent eigenvectors that go with it, whereas 5 just has one. Okay, so because our system has n linearly independent eigenvectors, n linearly independent eigenvectors, in this case n is 3, we can write our solution set. We can write our, let me just say, write our general solution. Write our general solution in the way that we talked about in the last video. In the method, well, let me say, in the form described in the last video. Okay, so our solution x of t is going to look like, so some constant c1 times e to the first eigenvalue, -1 t, so the -1 is the coefficient of t, multiplied by its eigenvector, which is -1, 1, 0, but there's another eigenvector that goes with -1, so I write that as well. So I have c2 times e to the -t, and then I write the other eigenvector, -1, 0, 1, and then we have one more, so we have c3 e to the 5t for this eigenvalue times its corresponding eigenvector, 1, 2, 3, and that is the general solution right there. So what part B asked us to do was to write the fundamental matrix for this system. To do that, let's take our general solution and write it in matrix form. So if we think about what we have here, we have a linear combination of a bunch of vectors. So we can write this as x of t equals, so the first vector has this -1, 1, 0 being multiplied by e to the -t. If we were to distribute the e to the -t in, we'd get negative e to the -t, and then we'd get e to the -t, and then we'd get 0 for the next entry. Okay, for the next column, e to the -t is also going to get multiplied in. So we'd have negative e to the -t, 0, and then e to the -t. In the next column, e to the 5t would get multiplied in. So we'd have e to the 5t, 2e to the 5t, and 3e to the 5t. Okay, and this is going to get multiplied by the vector that has c1, c2, and c3 as the entries. So those weights of this linear combination, they become the entries of this vector. Okay, so this matrix right here, this is our fundamental matrix. The fundamental matrix has all of the n linearly independent solutions. So here was one, here was the second one, here was the third one written as the columns. Okay, so let's just write it a little bit more explicitly. So our fundamental matrix, the notation to denote a fundamental matrix is we usually write capital X and then of t. And now let's just copy down what it was. It was negative e to the negative t, e to the negative t, 0, and then negative e to the negative t, 0, e to the negative t. Last column was e to the 5t, 2e to the 5t, and 3e to the 5t. So that was our fundamental matrix. So a couple of important remarks about this fundamental matrix. So because these columns are linearly independent, the determinant of this matrix should not be 0. So in other words, this matrix should be invertible. And the other important thing about this that I want to mention is this matrix satisfies the equation. If we were to take this matrix, its derivative, that would be equal to A times this fundamental matrix. All right, so let's go ahead and box this. So this was our fundamental matrix. So now let's solve that initial value problem. So this was part C. So in part C, we were given that x of 0 is the vector 7, 7, 16. So in an initial value problem like this, we use this initial value, x of 0, to find these unknown constants, the C1, the C2, and the C3. So we're going to use x of 0 to find the CI's. Okay, so when we see x of 0 being equal to 7, 7, 16, so this is true if and only if. So when we plug 0 into the left-hand side of our general solution, what we'd have is we'd have C1 times the vector negative 1, 1, 0, because the e to the 0 becomes 1, so that goes away. And then we'd have plus C2 times the vector negative 1, 0, 1, again, because the e part goes away, because e to the 0 is 1. And then plus C3 times the vector 1, 2, 3. So that's what we get by plugging 0 in. And that needs to be equal to 7, 7, 16. So plugging 0 in to our general solution should make it equal 7, 7, 16. All right. So at this point, we have a linear combination of some vectors on the left-hand side. We can rewrite that in matrix form. So in matrix form, the columns would be negative 1, 1, 0, negative 1, 0, 1, and 1, 2, 3. That matrix multiplied by the vector C1, C2, C3 should be equal to 7, 7, 16. So this is just a matrix problem. And we can solve this by forming an augmented matrix. So we'd augment negative 1, 1 with 7 for the first row, 1, 0, 2 with 7 for the next row, and then 0, 1 augmented with, 0, 1, 3 augmented with 16 for that third row. All right. So from here, it's just a matter of row reduction to find what the solution to this would be, and then writing down, and then plugging back in for what C1, C2, and C3 are in our general solution. So I'm going to skip that computation, and I'm just going to jump ahead to what the solution would be, because from here, it's just a matter of row reduction, and we've done row reduction a bunch. And that's not really the heart of the problem. It is most of the computation of the problem, but it's not the key idea behind it. So I'm going to skip this row reduction here. So at the end, I end up with this matrix here. And now I can write down what C1, C2, and C3 are. So we get that C1 is negative 3 from the first row, C2 is 1 from the second row, and C3 is 5 from the third row. So recall also that the general solution had this form. So now we're ready to plug in for the CI's. So let's plug in the CI's. So if we do that, we get that x of t. So C1 is negative 3. We get negative 3 e to the negative t multiplied by negative 1, 1, 0. C2 is 1, so we just get plus e to the negative t times negative 1, 0, 1. And then C3 is 5, so we get plus 5 e to the 5t times the vector 1, 2, 3. And that would be our solution to the initial value problem. So I want to end this video now by recapping what the solution to these matrix ODEs looks like, depending on how many eigenvectors that we have. So here is our recap. When we're solving this matrix ODE, x prime equals ax, we're going to be dealing with the case where A has n linearly independent eigenvectors, pretty much exclusively. So that's not always true about matrices. This is true whenever A is diagonalizable, so when A has n linearly independent eigenvectors. That's equivalent to saying that A is diagonalizable. We're going to be focusing on that case pretty much exclusively. Then the fundamental solution set, so in other words, a set of n linearly independent solutions to our matrix ODE is this thing. E to the r1t times u1, comma, dot, 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 up until e to the rnt un, where the ri's are eigenvalues, and the ui's are their corresponding eigenvectors. Okay, so when we have n linearly independent eigenvectors, we can form this solution set that has n linearly independent solutions. But the natural question is, well, what if we have less than n eigenvectors? If we had less than n eigenvectors, we could still form some linearly independent solutions like this. We just wouldn't have n of them. But the solution space is supposed to be n-dimensional. So how do we get our remaining solutions? So this is the topic of section 9.8, and it involves a concept called a generalized eigenvector. So when we don't have enough eigenvectors, enough linearly independent eigenvectors, we have to use what are called generalized eigenvectors.